Thank you so much. It's really a pleasure to be here this morning to talk to you all a little bit about the Snowmass process that's going on, and then some of the efforts that are behind our thinking in working on a complementarity white paper for this particular effort. So let me start by describing for you what the Snowmass process is and why we even have it in the US. So essentially, this is part of the US strategic planning process for particle physics. It's approximately a year-long community-wide study. Traditionally, this took place over a month or two period in Snowmass Village in Colorado. But as it's grown, the amount of science that we're doing and the studies that we're working on is turned more into even before the pandemic, a virtual process where people worked year-long having workshops and working on white papers, and then coming together at the end of the process, at the end of the year, to come together in person, having a workshop to put together the final papers. And the basic idea is that we wanted to find the most important questions for the field and promising opportunities. And then this results in a series of white papers and summary papers that are then input into a process called P5. This is another year-long process. It's the Particle Physics Project Prioritization Panel. And this is a panel of the DOE and NSF whose mission is to formulate a 10-year execution plan for the field of particle physics. And it's supposed to be really long-term. So the idea is that the vision is a 20-year vision and that you're formulating a plan for the next 10 years. And so just how this fits into sort of the effort. So this is something that essentially is happening every decade. And as you can see, similar types of efforts happen in Europe. And so currently in the US, we're working in particle physics off of the 2014 plan. And we're now starting the process of developing the 2023 plan. Particle physics is global, so the Snowmass process itself is sort of an international community. You don't have to be a US particle physicist in order to be involved in the process. And we certainly look at the international community and their strategies and plans from other regions to try to make sure ours fits together. As you know, particle physics, as this symposia is showing, is not an insular sort of process. It's a global, worldwide effort when we're trying to answer some of these questions. And so just within the US, this is sort of where we are right now. So this is a timeline of the process in the US, with this being 2020, and 1 representing January, 12 representing December. And so we spent quite a bit of time earlier this year and last year preparing for the Snowmass process and preparing to get ready to do this year-long study. And since about mid-March, we've been formally in the Snowmass process. And so that will last through sort of mid-October next year. The National Academy of Sciences will, within this time period overlapping with the Snowmass process, review the field. This is something that they do every 10 years. And then in 2022, the P5 committee will meet and do their studies and come up with final results. All right, so going back to Snowmass, that's sort of the overview of why it is we do Snowmass and how it is we do planning in the United States. So I want to point you to this website, snowmass21.org. This is where you can find all information about everything that's going on in Snowmass and all of the different projects and groups that we have going. But currently, what we have is we have 10 frontiers. So energy, neutrinos, precision, rare and precision measurement, the cosmic frontier, where much of dark matter, particle dark matter resides, when you're thinking about direct detection and indirect detection, and so forth. The frontiers each have 3 conveners. So we have 30 conveners at the top level of the frontier. And then each frontier itself has something like I don't know, about 7 or 8 topical working groups. So within each of these facilities or each of these frontiers, there are these topical working groups. And so we have about 250 topical group conveners. Okay, in addition to that, because there's a lot of overlap going between the frontiers, we also have 40 interfrontier liaisons. And then we want to keep young people, early career people involved in the process. So we also have early career liaisons. And the one thing I want to point out that is very, I think, poignant for this particular symposia is that every frontier, every one of these 10 frontiers has at least one topical working group that addresses dark matter in some way. So dark matter is one of the big interests right now in our community. This is just to give you an idea of the timeline and the process of what we've been going through. So we started in April with a virtual kickoff town hall meeting at APS. And from April until the end of August, we were collecting letters of interest. In addition, these 10 frontiers and topical working groups were having meetings and workshops. All of this building up to October 5th through 8th, where we had a community planning meeting that again was virtual and lasted several days. And the focus of that meeting was primarily interfrontier topics. So now we're sort of in this process here where we're putting together contributed white papers. So these are white papers by groups of people talking about what they think is most interesting. And it also includes some summary white papers that the different topical working groups think represent, based on the previous meetings, the letter of interest, and the CPM, what the main thrusts in the field might be. And so those papers will work on through sort of the end of July. And then eventually at the end here, next October, we would have the Snowmass report. Our hope is that our community summer study in July will be in person, but if that's not possible, we'll do it virtual and keep the schedule as is. So just to give you an idea of how big and massive this process is, this here is basically the number of paper counts versus frontier. We had 1,574 LOIs that were submitted before the August 31st deadline. And just as an example, so I'm one of the co-conveners for the Cosmic Frontier Subworking Group 1, which is particle dark matter. We received 150 LOIs. And so what we've been doing is we've been corralling those LOIs, and then based on what came out of CPM and the discussions there, we've corralled these into essentially about 10 big question white papers that we're hoping to solicit and get input from the community on. So each topical working group is going through a similar process of sorting the main ideas that would be addressed in white papers for their group. And then in addition to that, we're going to have at least one cross-frontier paper that addresses the complementarity for dark matter detection. We're still in discussions of whether this would be one paper or maybe that it would be multiple papers. It's a really big topic with a lot of interest. And so we're still in the process of trying to sort out what is going to be the best way to present the complementarity. Okay, so with that in mind, I know that we've already had a lot of talks, so I just want to transition now to how it is that we detect dark matter. And traditionally for detecting particle dark matter, we think of it sort of in 3 terms. We either shake it by direct detection, where we have dark matter interacting with a standard model particle and directly detecting that interaction. Break it, which is sort of more indirect detection, where we have either the annihilation or the decay of dark matter particles into standard model particles, which are then detected in detectors, or potentially we can make it. And so this is the idea that you would do at either an accelerator or collider, where you would take standard model particles, collide them together, and your output would be dark matter particles. And so now I just want to go and show a few examples. So I obviously in this sort of talk can't address every experiment or every idea, but I just want to give a flavor of how this works and what the strengths and weaknesses of the various techniques are as a motivation as to why it is that we need complementarity. So in colliders, you want to think about how it is that you might detect dark matter. So dark matter to a collider is essentially an invisible particle. And invisible particles are things that they do know how to detect at colliders. So you start with some sort of baseline assumption. So let's say that it's WIMP dark matter, and that WIMP dark matter then interacts with standard model particles that we can produce and detect at something like LHC or keck, or perhaps a future ILC, click, or some other experiment. These are all ideas and processes that are being worked on at in various frontiers. So the rare processes frontier, the energy frontier, and the accelerator frontier are all thinking about these things. So if I have a dark matter detector, so this is the Atlas detector here as an example. The basic idea is that if I have two protons, they come together, they interact, they produce visible particles. And the detector itself covers all solid angles. So ideally, you're catching essentially all of the visible particles. But dark matter doesn't interact in any significant way in the detectors. So it means that you need to be able to detect invisible particles. So how is it that you identify an invisible particle? The signature of invisible particles in experiments at the LHC is missing transverse momentum. So essentially, is there momentum that you're not identifying in the experiment that might be missing? And so an example of this is a monojet event at Atlas. And so the idea is that you would get a jet or a photon or a vector boson. And with that, in addition to that, there would then be some missing transverse energy from escaping non-interacting particles. So in order to use this technique, you really have to know the background of your detector. So the background shapes, they need precise theory predictions. And then of course, you need a model in order to interpret that missing energy. So the results can be interpreted by a variety of models. And in the examples here, this is a vector mediator that's being used to get an interpretation. So there's another way that you can use colliders or accelerators in order to look for dark matter. So if there's a force other than gravity, then you have to have a mediator or a portal, and the LHC could detect its decays into visible particles. And so that's represented here. So simplified models are very popular in collider and accelerator benchmark searches. And here's an example of a paper all about this topic that came from the LHC Dark Matter Forum and Working Group. And so this is also being addressed in the energy frontier and in the rare processes frontier. But of course, we want to be very careful of simplified models. It's sort of that goes back to that joke that if you start with a spherical cowl of uniform density, while ignoring the effects of gravity in a vacuum, you get some kind of result. So you want to be really careful of simplified models, but it is one way that you can go about making progress. So in addition, you can go beyond just having WIMP dark matter with light particles and very feeble interactions with the standard model. They benefit from high intensities, not only high energies. So in an accelerator, you can also have dark matter interacting with standard model particles. So we can then produce them and detect them at experiments like the SPS. So these are all sort of planned experiments. So you could have LDMX or SHIP. At the LHC, you have phasers. You could even do it in neutrino experiments, like using the Fermilab booster and mini boon. And then there's lots and lots of ideas. And so in Snowmass, this is also being addressed and looked at by the rare processes frontier and the neutrino frontier. So that might lead you to believe, as I've run through this, that somehow using colliders and accelerators is some kind of panacea, and we don't need anything else. But colliders and accelerators can't do it alone. And there's a couple of reasons for this. The first reason is that there are dark matter models that are not accessible at accelerator energies. And so this is something that the Cosmic Frontier, their subworking groups 1, 2, and 3 are looking at. And the second reason is that dark matter discoveries need complementary experiments. Direct and indirect detection can discover dark matter with cosmological origins, where you can't do that in an accelerator or in a collider. So this sort of leads us into direct detection, and I know we already had a lot of talks about that today, so I'm not going to really dwell on it. Here I just show sort of 2 examples of direct detection experiments, but they are not the only ones. So the xenon experiment, essentially you have large volumes using noble gases like xenon or argon. And we already talked about those in that session, so I won't say anything more. Or you could go with like a solid state technology like super CDMS. This is a smaller volume. This type of technology tends to go towards lower thresholds and lighter mass dark matter. And like I said, there are lots of experiments that are either operational or planned for this decade. And essentially, we're looking at generation 2 experiments that are coming online now, to G3 experiments, which hopefully will happen in the next decade, and then new initiatives in small projects in dark matter, which is another area where expansion into low energy, even lower energy dark matter particles is being investigated. And this is all sort of the regime of the Cosmic Frontier Subtopical Working Group 1. And so just kind of looking at where we go, roughly speaking, this is what we've excluded in phase space. This is our neutrino fog. And generally speaking, although not entirely strict, your cryogenic detectors will get you lower thresholds with higher resolution. And the liquid noble detectors can kind of go after these high mass, low background experiments. So I had also mentioned that there are these new initiatives in dark matter as well. So direct detection for very light dark matter is sort of a new area that is opening up. And again, here you're seeing the cross section versus WIMP mass. This is sort of where our existing constraints are. And looking down here, there are now ideas and different types of experiments that are either in some sort of R&D phase that are looking to open up this parameter space. So historically, these direct detection experiments were not sensitive to these very low mass dark matter masses. But there have been a lot of advances in technology and input from theory that have made this lower dark matter space not only accessible, but also an interesting region to probe. And you can do this often using a relatively small mass detector. So the detectors now can be made to be sensitive to lower thresholds. And a great example of this is this idea of having a phonon-based calorimeter. You can also look for subdominant effects that enhance signals in detectors. And I know that already at this symposia, you've talked about the Migdal effect and Bremsstrahlung. And then also there are new materials and detectors. This has resulted from the collaboration of astroparticle physicists in solid state physics and also quantum information systems. And we actually had a whole session at the CPM meeting talking about these new technologies. Again, this is something that fits in the Cosmic Frontier Working Group 1. So if you're searching for rare and rare dark matter, there are major updates that are planned for existing experiments that include larger exposures. Ingenuity in sensors, instrumentation, and materials are all making this possible, and also the understanding of our backgrounds. The one thing I want to point out is that there is this, what we are now starting to call the neutrino fog, a place where solar, atmospheric, and cosmic neutrino scattering may become larger than dark matter cross sections, but you still have this irresistible or irreducible background. And the reason that we've gone from calling it a floor to a fog is that at this point, irreducible backgrounds have never stopped anyone in the past. It may be shooting ourselves in the foot if we think that that's going to happen with the neutrino background. And over here is sort of a plot that shows essentially, if you have this reference limit, what happens as you increase the exposure, what a smaller target or nucleus would give you versus lower threshold limit. And then the question is actually, what if we discover something in direct detection? Then we would want some complementarity in experiments in order to confirm any kind of discovery. Now, another way that we do detect dark matter is through indirect detection. And I know that this will be the subject of the symposia tomorrow. So let me just briefly say, the idea here is that dark matter annihilates or decays in places like the galactic center or dwarf galaxies. It decays to some kind of particle. It could be a photon. It could be neutrinos. It could be whatever. And then those are detected by an experiment like Fermi or Hess. So you do this through experiments that use the direct detection experiment technique like Fermi-Lat or CTA. And then you have surveys such as the LSST that are able to probe the properties of dark matter and test dark matter models and help us to understand the astrophysical backgrounds. This is all understanding where it is that we find this, sort of these, we call them astrophysical probes of dark matter, is the regime of CF3, where how to detect the actual particle is part of the regime of CF1. And so the reason, of course, that we think about indirect detection as having some issues is that we have multiple examples now, and I've just picked two of them, where we've seen excesses of events that could be interpreted as dark matter from indirect detection experiments. So one is the GeV excess at the galactic center. The second is the 3.5 keV X-ray line that's seen in multiple galaxies. It was first seen in the XMM Newton data. And in both cases, you could interpret dark matter. In the case of the galactic center, this could be, there are lots of studies that suggest that it could be a dark matter particle of order 10 to 100 GeV. But that kind of idea is sort of in tension with the non-detection of dark matter coming from dwarf galaxies. And then in addition, there's evidence that you may be getting a large contribution to pulsars or Fermi bubbles or other sorts of backgrounds that are not as well understood or modeled. Similarly, with the 3.5 keV line, the simplest dark matter solution is probably a 7 keV stereoneutrino, but you also have possible astrophysical backgrounds like atomic lines that could also explain it. So in this case, none of these are smoking guns that a dark matter particle has been detected. And so complementarity, this is the idea. And so one of my colleagues made a word cloud by looking at the frequency of words in the LOIs that were submitted for Snowmass. And basically what you're seeing here is that the larger the word, the more often it was mentioned. And I think what stands out really here is that dark matter clearly is the most popular word that's being used in our LOIs. Since the last Snowmass, there's been a fundamental shift in how we think about searches for dark matter. During the last Snowmass, dark matter detection was in one frontier, it was in the cosmic frontier. And we essentially had a small number of working groups working on it, essentially one or two. And that's not what's going on now. The complementarity paper that came out of Snowmass last time was from within the cosmic frontier. Now it's elevated up to a higher level where it's crossing frontiers. And so we're in an exciting phase right now where new ideas can be implemented on shorter timescales. And as I mentioned, this dark matter is going across every frontier. But in order to get the full picture, we really need to combine this information. And then another thing that we've been thinking about, and that I think we really hope as people who are interested in dark matter, is that could it be that dark matter is the focal point of this Snowmass report, and perhaps is the most important, if not one of the most important questions for the next decade? So really where we are right now is we're trying to understand how it is we should portray this complementarity. And there are some issues with that, which I'll discuss on the next slide. If you're interested in complementarity and you'd like to join our effort, one way that you can get more information is to join our email list, snowmass-dm-complementarity@fnal.com. And if you go to the snowmass.org/cosmic/start website, you'll have information on how to join that email list. All right, so here's where we are in the current status. You know, we're just starting this, so unfortunately I don't have a lot of plots to show you. As a matter of fact, we're still even thinking about like an image that we could use that represents complementarity in a way that messages it to the outside world the way we want it portrayed. So we're developing guiding principles to organize this white paper. We need to tell a coherent story that gives the breadth of dark matter candidates and numerous experiments without making it sound like we have no clue what we're doing. And so we're just doing something scattershot and looking everywhere. So one way that we're thinking about doing this is using case studies that can be answered by joint work across frontiers and experiments. So we want to avoid the one-size-fits-all approach. We're looking at ways to highlight the need for work in multiple frontiers without looking like we don't have a unified strategy that is just some kind of scattershot effort. So we need to make an argument for broad and comprehensive search strategies without singling out one technique as a panacea for all dark matter searches. So the path forward, the search for dark matters, even WIMPs, isn't over yet. And it's the perfect time to search everywhere, including for the rare and unusual. The much larger data sets and precision searches at accelerators and colliders are making this possible, along with new and improved detectors and techniques and backgrounds and analysis tools. Now and in the future, it's essential that our physics complementarity is happening across different experiments and different frontiers. It's needed. We need to understand the cosmological origin of dark matter and the nature of the dark matter and standard model interactions. And so if you're interested in getting involved, we have an email list for complementarity. We have the Slack channel. And if you're interested in any of the topics that I sort of briefly mentioned on and you want to get more involved in them, I encourage you to go to the Snowmass 21 website for more information on how to get involved in different frontiers or different subtopical working groups. And I'm going to flash to this next slide to say something. So this talk and all of this work certainly is not my own. There's multiple people who are working on it. And down here, I'm highlighting some of the early career people who have contributed to some of our initial thinking on this. So thank you to those who contributed to this work. And then I'm going to go back to this slide in case people want the information on how to get involved. Thank you.